All right, so now going into lesson 3.2 here. Okay, so we went from understanding just what polynomials mean in general, what are those expressions, and some basic introduction type material. Now we're gonna look at how do we actually divide polynomials. All right, and basically, we can go through this really long drawn out process of trying to factor and then solve and then do all these other things, or we can learn a new shorter process for dividing polynomials that we're going to be able to use over and over again. Okay, it's going to be similar to the tricks that we use for solving the polynomials without plugging into our calculator. So again, we're going to explore those two theorems so that we can divide polynomials and try to make this a faster process for us. Okay, so titled synthetic doesn't mean fake. Okay, so if we go back through here, it's going to be based a lot, one of the theorems is going to be based a lot on long division. Okay, so I want to have us watch this video together to remind us what long division actually is, because I know it's probably been a while since you've had to do this. All right, so if we have the problem here, it's 1756 divided by 23. Okay, so this is your dividend and this is your divisor, or the thing that you are going to divide by. All right, so then when you're writing it there, right, our formula looks like that, right? So the divisor's on the outside, you have that dividing line, right, our long division line, and then you have your dividend underneath, okay? And then you've got to figure out, does 1 divide into that first term, okay? Or sorry, does 23, or does the outside term divide into the first value here, right? And since we can't divide 1 by 23, we've got to add on the next one. So we've got 17. Okay, does 17 fit into 23? The answer is still no. Okay, so we have to back it up even further, and we have to look at 175. Okay, so then we have to figure out, okay, how many times does 23 fit into 175, either evenly or nicely, right? So we can fit 7 23s into 175. Or if I do the next step here, which is 7 multiplied by 23, that gives us 161. Okay, so then we subtract. We have 14 left over. Obviously, 23 doesn't fit into 14, so we have to carry down that last value there, which is our 6, so we have 146. All right, and then we have to figure out how many times does 146 fit into 23. All right, and the answer is 6 times. All right, minus 138. All right, we have 8 left over, and that's our remainder. Okay, and we could even go a step further if we actually needed to, and that's when you would get into your decimal places. But if we were saying the answer to this, so 1756 or 1756 divided by 23 gives us 76 with a remainder of 8. Okay, and again, this is going to be important because it's going to help us figure out how to divide polynomials using this kind of shortcut method here. All right, so now when we look at dividing this polynomial, right, we talked a lot about, when we were doing expressions earlier, we talked about multiplying by the reciprocal, right, multiplying by the reciprocal or multiplying by its coordinate pair, sorry, not coordinate pair, complementary pair. Right, so we talked about multiplying this by x plus 1, right, on top and bottom, but then it got really complicated, especially when you consider that, you know, this top here has already 4 terms. So trying to multiply all 4 of those terms by another whole factor just gets really complicated really quickly. So what we can do here is we can actually work through the process of long division, similar to what we just did, but we can now use this to divide our polynomials by other factors, or factors not just single values. Okay, so again, we still have our dividend, we still have our divider, and then we write it in the same format we've used forever. Okay, And then we got to determine how many times the leading term, okay, that's the key there. The leading term of the divisor x goes into the leading term of the dividend. So leading term of our divisor is x. How many times does that go into this first term, okay? And we know that x goes into x cubed, x squared times, right? Or when I multiply this out, x squared, if I just focused on x for a second, x squared multiplied by x would give me x cubed, okay? And I know your initial thought might be to say, oh, it goes in 3 times. Well, if I wrote a 3 here, 3 times x would give me 3x, not x cubed, okay? So when I multiply out x squared by this quantity, x minus 1, I get x cubed minus x squared, all right? And then I have to subtract the entire quantity, all right? And notice, okay, notice, they put a parentheses around it because you have to subtract the entire quantity, all right? And that's a thing that we might mess up. So I want to make sure I'm really focusing on it. You have to subtract the entire quantity because this then becomes a positive. It doesn't become a negative, all right? So I end up actually having 5x minus negative 1x squared, right? So plus a 1x squared, right? That gives me 6x squared, all right? So then I look at bringing down my next term there. All right, I look at bringing down my next term. Since, again, the reason is because I have 2 terms here. All right, so since I have 2 terms here, I have to make sure I bring down that second term. So I'm looking at 6x squared minus 2x. All right, and again, even though I have these 2 factors here, I'm still looking at how many times does x go into 6x squared. How many times does that happen? All right. And so x goes into 6x squared 6x times, right? So I write plus 6x. All right. Then I get to multiply 6x by that entire quantity. All right. Then I do my subtraction. Again, reminding to put in parentheses the entire quantity, okay? Because I'm going to end up with negative 2x plus 6x. So that's going to give me 4x left over. All right, I carry down my 7. All right, I carry down my 7 to the bottom there. So I've got 4x plus 7. And then again, I'm going to figure out how many times does the first term in the dividend, so how many times does x go into 4x, right? And that's going to give us 4. So we're going to have x squared plus 6x plus 4. All right, and then when I multiply my 4 by that quantity, if I can skip forward here, I'm left with 4x plus 7, or sorry, when I multiply by the quantity, I'm left with 4x minus 4. All right, again, I have to subtract that entire quantity, which changes the sign. So now I have 7 plus 4, right? 7 plus 4, and that's going to give me a remainder of 11, okay? It's going to give me a remainder of 11. So when I rewrite this here, I'm going to have this quadratic, okay? So now this is a quadratic, and I'm going to have plus 11 over x minus 1, right? Because just like we do with math, or just math with numbers, we have to still address the remainder. We can't just throw it out. Okay, so what this would turn into is 11 over x minus 1, right? So the remainder divided by our divisor. All right, but this is a lot nicer to deal with than that guy there. Okay, and so this is a really, really quick version. I know it didn't seem quick, but I wanted to make sure I stopped and pointed out some highlights. But this is a quick version of how to divide polynomials and to make it into something a little bit more manageable, especially if when we divide our polynomial, we can get rid of that remainder term, or make it, again, something much, much more manageable here. All right. So now here, okay, you're going to encounter a problem that's maybe a little bit trickier here. So it doesn't look much trickier right off the bat, but we have to look at the fact that it's x squared minus 3 divided by x minus 4, okay? And something that I noticed right off the bat is that this top quantity is missing an x component, right? It's missing an x component, all right? So we'll watch this video here for this division example and see how they address it, all right? So dividend divisor, when we write it over, okay, x minus 4, okay? And just like I said, we're missing a linear term in the dividend. So you have to write that in, okay? And that's making sure that you put your polynomial in that standard form. So just like we did with quadratics, you have to have it in standard form. Otherwise, it's going to cause a lot of issues here, all right? So now x goes into 2x squared, a total of 2x times, right? We multiply the quantity to 2x by x minus 4, okay? That gives us minus 8x. All right, now we've got to make sure that we're subtracting the entire quantity. So that ends up adding 8x to it. All right, then we bring down our negative 3. So we've got 8x minus 3. And we look at how many times does x go into 8x? Well, that would be 8 times. Right, so that's going to be 2x plus 8. All right, then we multiply 8 by the entire thing. And we're going to have our 8x minus 32. Okay. We subtract that quantity, so that ends up negative 3 plus 32, okay? Plus 32, which ends up with a remainder of 29, okay? So our final expression should look as 2x plus 8 plus 29 over, plus 29 over x minus 4. All right, plus 29 over x minus 4. Okay, so again, what made this problem slightly more complex is that we have to put it in standard form there. All right, so that's what you got to check out before you can move forward with the problems. All right. Okay, so sometimes when we're doing this, the problem's just too long there. All right, so first off, if we're looking here, we've got 6x cubed plus 10x squared plus x. Okay, so this is in standard form here, but when we look at the bottom one, we've got 2x squared minus 1. Okay, so we've got to adjust the divisor in order to get that in standard form. All right, so we've got to adjust the divisor into standard form. But when we do that, we're going to find out that all of a sudden this problem gets really kind of long, kind of quickly. So again, flipping that over. All right, setting our process up the way that we normally look at it. We're missing that linear term in the divisor, so we got to make space for it. Okay, great. We add a 0x. So then 2x squared goes into 6x 3 times. All right, perfect. 3x. But that brings us all the way over here. When we multiply this entire quantity out, okay, we get 6x plus 0x squared minus 3x. Okay, now again, we're subtracting the entire quantity. All right, so that ends up giving us a new value of plus 4x. Okay, so then we bring that last term down there, and then we got to figure out again how many times does 2x squared go into 10x squared, and that would be 5 times. All right, so plus 5. When we multiply everything out, we're going to get 10x squared plus 0x minus 5. All right, then we subtract the quantities. Again, making sure we are careful with our negative signs. All right, so we're left with 4x plus 12 as our remainder. All right, 4x plus 12 as our remainder. All right, and I love what it says at the top here. This problem can be solved using the same process as the previous one. It just takes a little bit of time and patience. All right, so again, we can turn our longer equation here, potentially our more complicated one, into something a little bit nicer. Okay, so 3x plus 5 plus, and then we have our remainder here, 4x plus 12 over 2x squared minus 1. Again, it is slightly nicer there. Using our long division. Okay. And then the next process that we can deal through here is this thing called synthetic division. Okay. And this is where it's going to look very similar to what we learned in 3.1 here. All right, so our synthetic division allows us to divide a polynomial of any degree by a linear binomial. All right, so again, any polynomial, any number of exponents there, but we can divide it by a linear binomial in the form x minus a, right? So again, linear is that y equals ax plus b. So if our linear binomial is in this x minus a, we can use this process called synthetic division. All right, and again, that definition here doesn't give you any more details than the words here. All right. And again, I don't know why they called it synthetic, but basically it's not a fake process. All right, you can really do it, and it's just as quick and efficient, that has the same results as long division, but it takes less time. But the key here is that it's only if you're dividing by a linear binomial. Okay, so if it's something larger than this linear binomial, or your binomial is not in the proper form, you still have to use that long division form, which, you know, I know it's a little unfortunate. All right, but if we can divide using this synthetic division, we use this process here.
Using long division, the process looks like this.
Okay, and this is what we just learned how to do. All right, oh, and if I...
In order to do this problem using synthetic division, you must first insert 0 terms for any missing powers. Now it's time to...
Sorry, pause. I wanted to go back here so you could see what the final equation looked like. All right, so...
In order to do this problem using...
All right, so the entire problem boils down to, again, that 3x cubed plus 6x squared plus 5x plus 16 plus this remainder, all right, which ended up being 24 over our original divisor there, okay? And again, highlighting that first things first, you got to make sure that both your dividend and your divisor is in standard form. So 4x to the fourth, x squared, x to the first, and then your constant. All right, so again, we had to add in that 0x cubed terms. We had to put that in standard form, otherwise it's not going to work out like we want it to. All right, so now if we're doing this process of synthetic division, we're still going to get to the same answer, but it might be a little bit easier since this is that linear binomial term. Again, linear because it's x to the first, all right, and binomial because it has 2 terms. All right, so again, that's where those key phrases from 3.1 are going to be really, really helpful. Okay, so linear because it's x to the first, and binomial because it's 2 terms.
In order to do this problem using synthetic division, you must first insert 0 terms for any missing powers. Now it's time to set up the problem. Simply write the coefficients of the dividend in order, starting with the largest. Be sure to include any zeros you added.
All right, same thing that we did for the replacement in 3.1.
Next, solve the equation, x minus 2 equals 0, and place the solution, x equals 2, on the left side of the vertical bar. At this point, you are ready to start the division.
Okay, again, you had to solve for the linear equation. So this originally looked like divided by x minus 2. Okay, so we had to solve for x. So if we had x minus 2 equals 0, then that means x equals 2, right? So that's where they got that 2 from.
Start by bringing the leading coefficient of the polynomial down as seen here. To fill in the next column of the problem, multiply the 3 from the bottom row with the 2, writing the result below the 0. Then add vertically, writing the result below. To fill in the next column of the problem, multiply the 6 from the bottom row with the 2, writing the result below the -7. Then add vertically, writing the result below. Now continue this process, multiplying the 5 from the bottom row with the 2 and writing the result below the 6. then add vertically, writing the result below. To fill in the next column of the array, multiply the 16 from the bottom row with the 2, writing the result below the -8, then add vertically, writing the result below. Now study those values in the bottom row carefully. Do they look familiar? They're the coefficients of the quotient polynomial you got using long division. And that 24 was the remainder. If you look carefully, you will see many of the other coefficients from the long division problem within the array. On the left side is the result of the initial long division problem you did. Pay particular attention to the coefficients in the problem. On the right, you can see the same problem completed using synthetic division. Both lead to the same answer, but the synthetic division problem can be completed faster and in less space.
Okay, so highlighting a couple things here that may not have been well explained if you didn't pick it up. All right, so again, this original term, this original 3 here came from 3x to the 4th power, all right? 3x to the 4th power. All right, when we get our answer here, you have to step it down a power. So this is 3x to the 3rd power. Now, this is 6x squared, 5x to the 1st. Okay, so knowing that this one started as x to the 4th, and then whatever answer you get gives us x to the 3rd. All right. Another thing here, the process of multiplying and carrying over and adding together, okay, that's the exact same thing that we just worked on in our last in the last unit for pre-calc, right? So, in the last unit that we just worked on yesterday. So that synthetic substitution, okay? So the process, once you set it up, is exactly the same, but the setup is what might be a little bit more confusing, okay? And yes, we will work on working through some of these problems together, okay? But it's all about the setup pretty much here in these problems, all right? So to show you another synthetic example here.
Using long division, the process looks like this.
Okay. And we'll skip through.
And place
okay.
Next. Process looks.
Sorry, pause. All right, so the process here, we have 2x cubed plus 4x squared minus x plus 6, okay? And that whole quantity is divided by x plus 3, all right? And you can watch this video on your own, but I want to point out a couple things just quickly. All right, first off, you've got to check to make sure that both of these terms are in their standard form. By that, x cubed, x squared, x to the 1st, done, all right? And then what you got to make sure is that this divisor, okay, is that linear term. So it's got to be x to the 1st power plus or minus some constant, okay? And when we do the long division, okay, we can carry that through. We know how to do that, all right? But when we come and we set up our problem here, okay, the setup is we carry our coefficients into that box, all right, including the constant term. So if you have no constant, you still have to write +0, okay? So that's part of putting this in that standard term, all right? And then we got this -3 because originally it was divided by x plus 3. So we had to solve for x, all right? But then again, once we're done with that, we carry it through and we do the exact same process, okay? We do the exact same process. All right, but you can go through and watch that video if you want. All right. Now, the catch for that one, as I already told you, it really only works if the divisor is a linear polynomial. All right. It really only works best when it's a linear polynomial, and truly it works best if it's x minus a. All right. But for non-linear divisors, you're going to have to stick with long division. So sorry, I know that stinks. But if it's linear, you can do the shortcut there. All right, then moving forward here, the first theorem we're going to learn about is this remainder theorem. All right, and what this remainder theorem is it's produced when you divide your function by your binomial. Okay. And that's what's saying, and we'll work through a couple examples here, but it says given a polynomial f of x of degree greater than or equal to 1, so it's not linear, right? It's linear or better. The remainder for the polynomial is k, all right? So what that looks like here is, in other words, if f of -3 is equal to -9, all right, f of -3 is equal to -9. All right. And how this works here, or what this is really saying is when I plug in and I want to evaluate if I divide by -3, if my remainder is -9, all right, my remainder is -9, and then what it's saying is if I actually plug in -3 into the equation and I solve for it, if my answer is the remainder as well. Okay, so I think they didn't do a super great job of showing this. So let me, right, so we're saying they're dividing that by x plus 3, okay? So you're dividing this quantity by x plus 3, okay? So again, you're going through that synthetic process, okay? Where when we solve for x, we get -3, okay? So if I write -3 there, awesome. All right, and then when I solve for this guy, I'm left with the expression 2x squared minus 2x plus 5 plus -9 over the quantity x plus 3, right? My original divisor. Okay, so that's what I'm left with when I do this. All right, so I guess I should say -9 over x plus 3. All right. And then when we look at f of -3, it also equals -9. All right, when we look at f of -3, it equals -9. All right. And how that really is useful is factoring it all in, right? So this factor theorem, all right, this factor theorem is talking about if the remainder equals 0. If the remainder equals 0. So if there's nothing left over, right, if there's nothing left over, then it perfectly fits in, which makes that a factor of the above expression. All right. So, and again, I know it's difficult when they write it in terms like this, but basically what this is saying is if I take f of x here and I divide it by this term x minus 1, so if I had this divided by x minus 1, if I'm left with 0 remainder, that means x minus 1 is a factor of this, right? So I could have perfectly factored this out. So x minus 1 is an entire factor plus whatever this is. So this would be a 3x squared minus 3x plus 2, right? So again, if I was factoring it, and let me annotate this for you guys so it's very clear. So the factors of that are equal to x minus 1 and what we ended up with as a result of our division. So our 3x squared minus 3x plus 2, okay? So, oh my gosh. Sorry, don't know what just happened there. All right, so those are two factors there. And again, x minus 1 is a factor because we end up with 0 remainder. All right. Okay, so then for synthetic division and factoring, okay, if we have a problem, given that x minus 2 is a factor, okay, we can show this expression by looking at, okay, if I've got f of x, I solve using either my long division or my synthetic division, okay? And then when I do my synthetic division, I have 0 left over. So therefore, you could say that x minus 2 is a factor, and so is this one, right? And then if it's something that we know how to factor even further, right? So we've done a lot with quadratics. We can factor that down even further, right? So then that means we've got 3 completely separated factors, and then we could solve from there even easier. Okay. And I know that was a lot, so let's take a minute here to kind of breathe and go over the answers to the study guide, right? And we'll work a lot with also the checkup and how that makes sense. All right. But for here, okay, the dividend is the value on top. Okay, the divisor is the value on bottom, obviously. And then for the quotient and the remainder, we would actually have to do the process. Okay, so you just write it in your normal long division format. And again, it's focusing on how many times does this first term fit into this first term here. Okay, so the first term of the divisor fits into the first term of the dividend. All right, and since this has two terms, every time we have to carry down, we have to make sure we have at least 2 terms there. All right. So then we're left with our quotient is x squared minus 8x plus 20. Our remainder is minus 45. All right. But if we were writing this as our equation here, it would be the x squared minus 8x plus 20 minus 45 divided by x plus 2, right? So the remainder is negative 45, but when we write it as an equation, you have to remember, you got to put the remainder over the divisor. All right. Same thing here, except the only difference that we pointed out was that this was x squared and it was missing that x to the first term. So you have to add that in as a 0x. All right. And this one again, you can try on your own. Because I want to make sure we keep on pace here. Now for page 5, this was again talking about the synthetic division. All right, and the only difference between the synthetic division and the synthetic substitution that we did yesterday was that this value here, in order to get this value, you had to actually solve for x of the divisor, right? So x minus 3 is the divisor. If I set this equal to 0, x is equal to 3, right? So I then make this 3, but then I carry through the exact same process, right? And my divisor, or sorry, my value that's left over in the bottom right-hand corner, where that was my solution yesterday, this is now my remainder. So my remainder is 56. And again, if I was writing this, it would be 56 over x minus 3. All right. And then again, if I have 2 here, like this was my 2x to the 4th, this is now 2x to the 3rd. You have to drop it down by 1 exponent. So I've got 2x to the 3rd plus 6x squared plus 10x plus 21. And then the final answer would also be plus 56 over x minus 3. All right. And then to put it into words here, the synthetic divisor can only be employed when the divisor is a linear polynomial, all right, especially in the form x minus a. All right. For nonlinear divisors, we have to stick with long division. All right. Now, for the first theorem there, the remaining theorem, that was where if we have our function here and we have x minus 4. So if we're dividing our function here by x minus 4, the remainder is equal to what happens when I plug in x 4. All right. So again, if I'm solving for my x value here, right, if I were to do my synthetic process here, my remainder would be whatever x, when I plug in 4 for x there, that is my value. Okay. And I totally understand that these theorems, especially this first theorem, is kind of difficult. I'm having a difficulty making sure that I'm explaining it to you properly. okay? But this will come in handy later on in this unit. So understanding just the basics of what it means is going to be beneficial because we're going to have to use that a little bit later, all right? So again, just knowing that the remainder of this product, okay, is equal to the same thing as if I just solve for x equals 4. All right, looking at this one, if I divided my entire equation there by x plus 7, right? When I do this synthetic process, x is equal to -7. So I would evaluate this based on -7. All right. And this theorem says is it works is if I'm dividing this and if the remainder is equal to the same thing as if I evaluated f of -7. All right. And then for the last one here, it's talking about factors. So is it a factor of something or not? And how you know is if you carry through this process or you carry through the long division process and your remainder is equal to 0. So if your remainder is equal to 0, then yes, it is a factor. Okay. And so then again, knowing that this is now a factor, okay, x plus 6 is your first factor. Then we're left with some kind of quadratic, okay, that you can further factor knowing all the rules that you guys have learned throughout this, okay? And I know that these ones for pre-calc are taking longer, but that's because it's, unfortunately for this one, we don't have a foundation on polynomials. Okay, so unfortunately, these ones are taking longer. So I'll definitely try to make sure that that for Algebra 2, we keep those really, really short if we can. Okay. So moving forward with this checkup here, all right. Moving forward with the checkup. All right, the first couple of here are using long division. Okay, and again, for the sake of time here, I just want to go through and give you the helpful hints for how to move through these faster or how to make sure that you're doing them right. So, all right, in terms of helpful hints here, all right, the first one would be to make sure both of them are in standard form. All right, so 1, put in standard form. All right, so if they're both not in standard form, make sure you change those to standard form there. All right. Then the second thing would then be obviously set up your division. Okay, so you have your divisor and you have your dividend. All right, and then you're going to continue to share, okay, you're going to continue to solve and making sure that you're carrying down your remainder. All right. And then you have to make sure you rewrite your equation in proper form. Okay, so you rewrite your equation in proper form. All right, and so what I mean by that is making sure that whatever your remainder is, you have to put plus your remainder over your divisor, right? You can't just leave that out. Okay, so if we do maybe 1 or 2 of these problems here, okay, I've got 5x squared plus 3 divided by the x minus 5. All right, well, first off, I have to add a 0x term, okay? Plus 3. And I'm saying that's divided by x minus 5. Okay, so that's in standard form, and we're good to go on that one. So what I can do is I can set up my equation, 5x squared plus 0x plus 3 divided by x minus 5. All right, and then again, in the first one, I'm looking at the first term in both of these, so x and 5x squared. Right, so x can fit into 5x squared 5x times. All right, so then I multiply this entire quantity. So I've got 5x squared plus, minus 25x. minus 25x. Now that's a quantity. So I end up having minus a minus, so I end up having 25x. 25x. Then I have to bring down my 3. All right, I have to bring down my 3. Okay, then x fits into 25x 25 times. So when I multiply out, I have 25x minus 125, and then I'm going to subtract the entire quantity. So I end up with a remainder of 128. Okay, so when I write my final answer, right, if I'm saying divided by x minus 5, my final answer is going to be 5x plus 25, so my answer on top, plus 128 over x minus 5. Right, so that would be my final answer. Okay, that would be my final answer. All right, and then potentially one of the weirdest ones you're gonna see. All right, I thought I'd skip to this one because it's kind of fun. 6x plus 5 divided by x plus 1. All right, so that goes in 6 times. Multiply by my quantity, 6x plus 6. Okay, when I subtract, I'm left with negative 1, right? So my final answer for this one is actually 6 minus 1 over x plus 1. Okay, so you can still make those slightly easier even if they seem pretty short there. All right, now for 6 through 10, this is using the synthetic divisor. Okay, so using the synthetic divisor. So I'll skip to number 7 here. All right, so first thing I check is it in standard form? The answer is yes, so we're good on that one. All right, and then I solve for my divisor. So if x plus 2 is equal to 0, that means x is equal to negative 2. All right, so what this is going to look like here is I'm going to plug in negative 2 in my top left-hand corner. All right, and then I'm going to plug in the constants or the coefficients. So I've got 3 for my x cubed term, 7 minus 13, and then positive 10. All right, I carry down my 3. 3 times negative 2 is negative 6. I add them together. That gives me 1. Okay, multiply together again gives me negative 2. I'm at negative 15. Then when I multiply those together, I've got 30. So added together, I have 40. All right, so this is, again, my remainder. All right, so my final answer for this one, this was my x cubed term. So this ends up being my x squared term. So I have 3x squared plus 1x minus 15 plus my remainder, which is 40 over x plus 2. 40 over x plus 2. Okay? All right. And there's plenty of examples there that you can work through. We'll do maybe one more here. We'll do number 10 since number 10 seems pretty long. Okay. So first off, I check 4, 3, 2, 1, 0. Okay, we're good. We're in standard form. All right. Then next is I solve for my divisor. So x minus 4 is equal to 0. So x is equal to 4. So when I set this up, I put 4 in my upper left-hand corner. And then I write all my coefficients. 8 minus 14 minus 71 minus 10 positive 24. All right. Carry down my 8. 8 times 4 gives me 32. Plus 14 gives me, or sorry, minus 14 gives me 18. Times 4 gives me 72. Minus 71 gives me 1. Times 4, 6. Oh my gosh, sorry, 4. Minus 10 gives me negative 6. All right, multiply those together gives me negative 24, and lo and behold, I have a remainder of 0. All right, so x minus 4 is a factor of the following expression on top. Okay, and again, this is my x to the fourth, x third, x squared, x, and then my constant. So my final answer here, when I write it out, this now becomes x cubed. So I have 8x cubed plus 18x squared minus 1x minus 6. So that's my final expression there. I have no remainder, therefore I don't need to add anything to the end. Okay. For 11 and 12, okay, 11 and 12, we didn't see any of these, so I'll walk you through 11 here. Basically, what this is saying is evaluate the functions f of 1 and f of negative 3. Or another way to think of this is, again, x is equal to 1 and x is equal to negative 3. So when you're doing this, it's like saying, okay, evaluate what would happen if I divided by x minus 1, or if I divided by x plus 3. That's what you're solving for here. Okay, is if I divide by these different functions, what's going to happen? Okay, so when I write out my synthetic divisor here, all right, I'm going to have the same for both. For negative 17. Oh, and I almost missed a step there. I'm missing an x squared term. So I've got 4x cubed plus 0x squared minus 17x plus 9. Almost forgot a term there. All right, so this is saying 4x cubed, 0x squared, 17x, and then 9. All right, so I'm going to have two of the exact same things because I'm evaluating the same expression. But what it's asking me to do is now evaluate for f of 1. So I put a 1 there, and it's telling me to evaluate for f of negative 3. All right, so if I do 1 first, 4, negative 13, negative 13, negative 4. So f of 1 is equal to negative 4. All right, and that's a super simple way of doing that. F of 1 is equal to negative 4. All right. And then when we do the other product here, okay, 4, negative 12, 36, 19, negative 57, negative 48. Okay, so my f of negative 3 is equal to negative 48. All right, and that would be how you could evaluate those different functions at those different values there. Okay, that would be how you could look at those guys. All right, so very, very similar to what we learned yesterday, and an adaptation of what we just went through this morning. All right. And then for 13 through 15 here, is the given linear expression a factor? Okay, so again, you would just factor, and then if there's a remainder, yes, not a factor. No, it's a factor. All right. So that would be those guys. All right. And I know that this section took a little bit longer than expected, so I'll try to speed it up for the next one here. Okay. All All right, so that is looking at dividing polynomials. All right, and personally, again, I think division can be the most difficult one, which is why I wanted to spend more time on division. All right, so right now you have the 3.2.2. The checkup we just went through, you only have this one quiz here. All right, so you only have this one quiz for this lesson. All right, so now when we go to the next section here, all right, we've got solving polynomial equations. All right, so when we're solving for them, again, we're just trying to use those theorems, those facts that we've learned, and in order to actually solve for the theorems, right? And if you look here, we're going to use that synthetic division to test for roots or test for factors, right? And then once we find those factors, we can then solve for our x-intercepts, right? Just the normal way that we've been doing that for quadratics, but now we might have more than just 2 x-intercepts, so we can solve for those. And we can then draw our graphs based on what we've already know about shapes and about what the end result's going to be based on our the values that we looked at in 3.1 there. All right. Okay, and we'll skip over this one here. Okay, so if we look at these two equations here, okay, so these two equations both have the same roots here, but obviously we're more comfortable with figuring out this top one here, right? We can use that zero product rule, saying that if all of this is equal to 0, then either this, or all 3 of them have to equal 0. So we can actually solve for that and figure out -3, 4, and +5. All right, but these two are the same expression. Okay, these two are the exact same expression, except the top one is the factored version. So again, it's all about getting to that factored version and figuring out how we can actually utilize that and plot those. All right, and same thing here. Okay, same thing. If we have these two expressions, okay, this one becomes a lot easier to look at than something where you're asking for 24x cubed, right? They all have the same zeros, but it's much easier for us to use the zero product rule in this top one once we've factored them all out. Okay. All right, so then if we look at this rational root theorem, okay, so don't let this confuse you. This is just saying you have to have that x to the nth power. You have to have x to the something term, and then every term after it has to be included. So if this was just x cubed and there was no x squared term, technically it's a +0x squared term. All right. And it's saying, let this be a polynomial function that has a leading coefficient not equal to 0, right? Same thing, a cannot equal 0, all right? So what we're saying is if x is equal to p over q, okay? If that's a rational 0 for the equation, then f of x is equal to 0 and x is equal to p over q is expressed in its simplest form, okay? So really confusing. What that boils down to is if I have x is equal to this, then y has to be 0, right? If x is this and y is 0, that makes it an x-intercept. It makes it an x-intercept, all right? And then what that tells us is this top factor here, p, is a factor of the a sub 0 term, right? So that leading coefficient, right? So it would be the 24 in this example. And then if that's also true, again, the variable q, the number on bottom, is a factor of the a sub nth leading coefficient. Oh, I'm sorry, I flipped those. Apologies. I flipped those. P is a factor of a sub 0, so the constant term. So P would be a factor of 10. All right, so 2, 5, 1, 10. All right, and then Q would be a factor of the a sub nth term, so that leading coefficient, so that would be 24, right? So 6, 12, 2, 4, anything that could make up 24 there. All right. So let's work through, if we look at a couple of problems here, okay, if we look at our problems, we'll watch this together here. Okay, so if we consider the polynomial, okay, we can do a shortcut here where we just try to do that P and Q version like we've been doing, but now P and Q get a little bit more complicated because we have to divide by them. All right, so if we are looking at P, all right, P has to be factors of the constant. All right, so that last term there. So P has to be factors of 8. So it can be 1, 2, 4, or 8. And you're going to notice it's plus or minus, because if I have -1 and -8, that's going to multiply together to give me +8. All right. And then we look at factors of Q. All right, or sorry, Q is factors of this first constant term. All right, so factors of 2. So we've got 1 and we've got 2 there. All right, so then looking at a different one here. All right, we're going to create the factors of P and factors of Q for this new one. So if we've got 12, we've got 1, 2, 3, 4, 6, 12, anything that can get multiplied together to give us 12. And then we have Q, which can be factors of 1 and 3. All right, so now if we are looking at the answer to that problem, we then can put every value of P over Q. And this one gets really, really large because we have multiple P and Q values, okay? But what we can do is we divide every single term on top by the terms on the bottom. So 1 divided by 2, 1 divided by 3, right? 2 divided by 1, 2 divided by 3. And then we delete or eliminate the repeating values, okay? So we get rid of any duplicates that we might see. So 12 divided by 3 is going to give us 4. Right, so we get rid of that. And these are all the possible rational factors of our equation, right? And this, again, is a larger list, but sometimes when we do this, we can get down to a very, very small amount of numbers. All right, and so then we work from possible to actual, right? So we've narrowed our list, and so then what we do is we narrow them even further. All right, so the next one here is the fundamental theorem of algebra. Okay, so what this is saying is a polynomial function of degree n has exactly n zeros as long as you permit complex numbers to be considered zeros. All right, so basically, if we have x to the third power, we have technically three zeros, as long as you let a complex number be considered a zero, okay? So you might only see 2 on the graph, but there are 3 actual answers. One of them would just be a complex answer. All right. And again, in plain English, you will learn that for a polynomial degree n, you will have n linear factors, which produce n zeros or roots. So again, if we had an x cubed, we will end up with 3 factors. Okay, and then each factor would give us a different 0 or a different root. Okay, you might not see them all on the graph, but they are there. Also, factors may be repeated. Okay, so a root may end up being 2, it may have the same number. So if you have x equals 2 and x equals 2, technically there are 2 zeros there at that one number. Okay, so just some things to think about here. All right. Sorry. So these are some really good rules that are in the study guide. So you'll definitely have them in multiple places. But talking about conjugates, right? Talking about those complex conjugates. All right. So what makes a conjugate, to remember, is if it's differed by only the positive or negative sign. So 3x plus 5 and 3x minus 5. They're complex conjugates because it has the only difference is that positive sign in the middle. 2 minus square root of 6, 2 plus square root of 6 are all conjugates. All right. So a polynomial with n degree has at most n unique roots. For example, okay, like I said, third degree polynomial can have 3 roots or 3 x-intercepts, zeros, whatever you want to call it. All right. Then you have this conjugate radical theorem. Okay. And this one is saying that if you've got 3 plus the square root of 2 as a root, then also 3 minus the square root of 2 as a root. All right, and we've talked a lot about that with the quadratics. Okay, so you already know this one. We're now just putting a theorem name to it. All right, and then it's the exact same thing for the complex conjugate. Okay, so this one actually would give you a real number. So if I typed into my calculator 3 plus square root of 2, it will give me a real number, right? It's going to be it's going to have decimals, but it'll give me a real number. Okay, this is the exact same theorem, except for now it's dealing with imaginary numbers, right? Those complex numbers, because it's got that a plus bi form. All right. So then here we're talking about the rule of signs. Okay, so the rule of signs, again, being really careful with positive and negatives, positive and negative values. All right. And they were developed by this guy named Rene Descartes. Okay, and those three main rules here is that the number of positive roots is less than or equal to the number of sign changes for the terms of a polynomial. All right. So the positive roots is less than or equal to the number of sign changes, right? So for example, if I have my quadratic here, I have potentially one sign change, okay? I have potentially one sign change if I am directly on my axes, okay? So I can only have one or less. So I can have less than or equal to one potential root. All right. If I move my my quadratic underneath, okay, up here I'm positive, then I'm negative, then I'm positive. Okay. So I have two sign changes. All right. And you're going to notice I have two roots, and that's fits along with this first rule here. The number of positive roots is less than or equal to the number of sign changes. I had two sign changes. It is equal to the number of sign changes. All right. The next rule there, also the number of negative roots is less than or equal to the number of sign changes for the polynomial f of negative x. Right, so if I have the negative values for x, okay, I can have basically the same thing except for in the opposite direction. All right, in each case, if the number of roots is less than the number of sign changes, then it differs by a multiple of 2. Okay, and they said it perfectly here. This rule is not going to seem clear at first, but we're going to apply it, and it'll make more sense as we go along. Okay, and then this one here is talking about bounds. Okay, so basically saying we have different reasons to make upper or lower bounds, and basically that's the constraints within your graph. Okay, so your upper bound is how far you can go in the positive direction, and your lower bound is how far you can go in the lower direction. Okay. All right, so almost done here. I know this one is a really meaty chapter. Okay, so if we're putting it all together, we've got Descartes' rule of signs and the upper and lower bound theorems. And when we look at how to actually utilize this, it'll hopefully make a lot more sense. So practicing these polynomial roots. Okay, so we take our original function here. Okay, we list all of our, the steps here is that we're going to list all of our rational roots, right? And that's our P's over our Q's. Then we're going to use Descartes' rules of signs to describe the nature of the roots, right? Are they going to be positive? Are they going to be negative? Are they going to be less than or greater than something? Okay, then we're going to find this thing called an upper bound. So the highest number that it can possibly be, and then we're going to find the lowest number it can possibly be in the lower bounds. And what we're going to do then is it's going to allow us to find our roots for this function. Okay, it'll lower the potential options for us here. So again, we're starting with all potential options, and then we're using these rules or theorems that we've learned or figured out in order to get rid of some potentials here. Okay, so what that really looks like. Okay, our root theorem here, okay, is where we take all the values of all the factors of the constant term over all the factors of the leading coefficient. And this one is actually awesome in my opinion, because look, your Q is 1. So you're dividing everything by 1. So it's not as many as we had when we were looking at, 12 and 4. So all our potential roots are plus and minus 1, plus and minus 2, 3, 4, 5, all the way up to 36. Okay, so that's step 1. Apply the rational root theorem. Okay, then we're going to use Descartes' rule of signs. All right, and this is another example, so not looking at it graphically here. Oops, sorry. Pause. Okay, so we can use Descartes' rule of signs graphically, or we can look at it with an equation. So for example here, I have a positive sign out here. Technically, this is a positive 1. Then I go to negative 4, so that's one sign change. Then I go back to positive, so that's another sign change. And then I go from positive to negative again. So positive to negative, one change. Negative to positive, another change. Positive to negative, that is another change. So I have 3 sign changes, okay? So I can have 3 or 1 positive real roots. Okay, I can have 3 or 1 positive real roots. Okay. Now, I can then plug in negative x, right? So that was that next rule. So if I plug in negative x into this equation here, okay, I'm then going to solve and simplify, all right? And then I'm going to look at where these signs change. Okay, so I've got negative, 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 negative. All right, so because all of those were negative, right, there was no sign changes. All right, so then what we can do here is we can evaluate all of those possibles, right? So since we had no sign changes, we have no negative roots. So it listed all of our possible roots here to just being all the positive values here, okay? And now what we're gonna do is we're gonna look for, we're gonna look for these upper and lower bounds. So what you can do is you can look for and plug in these values, right? So for example, they picked the value right in the middle. So checking the value x equals 6, you can tell that you're not getting a 0, right? So that ends up with 90, we're not getting a 0, okay? But we can also see that we have no sign changes, right? It doesn't go -1, +2, negative this, right? So they're all positive, all right? So this is telling us here that since we don't have any sign changes, okay, we don't have any sign changes, this is alerting us to this is potentially our upper bound, right? This is our upper bound here. Okay, and it says don't worry about checking 9, 12, 18, 36. I always check the one right above it. Okay, so I personally would also plug in 9 to see if I have any sign changes, because then if you do, you know you are at your upper bounds. Okay. So then we come in and we check the rest of the results. Okay, so we plug in 4 and we see that 4 ends up giving us a root there. Okay, 4 ends up giving us a root, and the reason we know it's a root is because it ends in 0. Okay, so again, okay, so we shrunk, okay, and we figured out that, hey, 6 was probably our upper bounds, okay, since it didn't have any sign changes, so then that eliminated 6 and above, all right? So then we had 1, 2, 3, and 4 left over. Okay, we had 1, 2, 3, and 4 left over, all right? Then what we can do is we can start working our way down. So now that we think that 6 was our upper bounds, meaning that's as high as we could go, and we checked that and it wasn't a root, we now work downwards. Okay, so again, we plug in 4. Okay, and we look at our 1, -4, 9, and -36. So when we plug that in, we find out, hey, 4 is a factor. All right, so since 4 is a factor, we can rewrite our original expression here now considering that 4 is a factor. All right, so 4 is a factor and that gives us x squared plus 0x plus 9. Okay, and then what we can do here is we can look at x squared plus 9. All right, and we know that we started with x cubed, right? Our original expression started with x cubed, which is what he means when he says the fundamental theory of algebra. Okay, so since we started with x cubed, we know we have to have 3 roots. Well, right here, we know that this x minus 4 is going to be a root. All right, now we have to end up solving for x squared plus 9. We have to solve for x squared plus 9. But we already know how to do that. All right, and this is going to end up giving us, though, x is equal to plus or minus that 3i. So it's going to give us that imaginary complex number. All right, so we're going to have 2 roots. X equals 4 and x equals plus or minus 3i. Okay, but we're only going to see one of them on the graph because these imaginary numbers don't show up on our graph there. Okay, again, if we start this guy over, again, the main things you need to realize are the steps, okay? So the main thing I want to highlight here is the steps. So you use the rational root theorem, the P over Q, to figure out all potential roots, okay? Then we look at, if we don't have the graph, we look at our equation here. Okay, we look for how many times it changes signs. So negative to positive, positive to negative. All right, and then f of x, okay, so f of x, if it changes, this one changed 3 times, so we could have up to or less than 3 real roots. Okay, we could have up to or less than 3 positive real roots. Since it had no negative, okay, since when we plugged in for f of negative x, come on, little tree. All right, so since we plugged in for f of negative x and we found out that it was negative, 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 and negative, there was no sign change. Okay, so since there was no sign change, there's no negative real roots. Okay, and what we mean by real is, again, it gives us a number that is not imaginary. Gives us no imaginary numbers. Okay, so another practice here. Okay. Okay, sorry. I thought the music would stop. So again, we're going to apply the rational root theorem. So again, all the factors of the constant divided by all the factors of the leading coefficient. All right. And again, this one gets not too terrible, except for the fact that we have now some uncomfortable fractions here. All right. And if there was any duplicates, we would get rid of them. All right. But we only have a couple of options here for our possible roots. Okay. So now once we've applied that rational root theorem, we're going to use Descartes' rule of signs. So we have no sign changes, right? It's positive 4, positive 9, positive 22, and positive 5. So there are no positive real roots. So what that means is we go in our list here and we get rid of all the positive numbers. So our roots are either going to be -1, -1/2, -1/4, -5, right? So on and so forth, since there's no sign changes. Okay, so then we look at f of negative x. All right, so we substitute in negative x, and what we actually find out here is we have negative, then positive, then negative, then positive. So we have three sign changes. So that means there's either 3 or 1 negative real roots. Okay, 3, 2, or 1 negative real roots. Okay, so then what we do here, so what we do here now is we follow that process that we've been doing. But again, I agree with the tree here, okay? I wouldn't worry about doing any of the fractions. I would stick with the whole number integers if you can, all right? And if they all end up being fractions, which they shouldn't be for this type of thing, but if you get into a real world situation and they all are fractions, what you're just gonna do is you're just gonna plug and chug, right? You're gonna try to see if you can figure out what these numbers are. Okay, so you're just going to plug in and see when you can get values to work. All right, now they plugged in -1. Okay, so since -1 has a remainder, it's not a root. Okay, that's the first thing you need to know. And it's not even a boundary, because you can see here we go from having all positive signs to a negative sign there. So that's not even a boundary. So now we've got to move in even closer. But since the only other integer is -5, we plug that one in. Okay. Now, when we plug -5 in, okay, it's not a 0. It's not a perfect root itself. Okay. And we have alternating signs. So positive, negative, positive, which means we are at a lower bound. Okay, which means that is as low as we can go. All right, so it's not super helpful, but that means that we don't go any smaller than -5. Okay, so we can't go any smaller than -5. So if there was an option for -10 here, because of this alternating sign here, we would know that we don't even try it out. Okay, so now, unfortunately, we've gotten rid of those two, so just picking and choosing. So whatever, the tree decided to pick -5/2. Okay, again, if it's not a root and it doesn't tell you anything about your bounds, then you can just keep trying. All right, then we tried -1/4 here, and great, finally we came to a root. All right, and hopefully it's not that terribly long that you have to try too many. But we know that there are 3 roots, because again, this is x cubed. Okay, so we know this is x cubed, so we know we have to have 3 roots. Rather, whether they're real or imaginary is going to be up to our first factor here. Okay, and so it's saying here, to find out if there's more roots, you can check the other 2 left over. So we can check the -1/2 or the -5/2, or we can factor out the -1/4, which we know is a factor, and then we can get our quadratic and use our quadratic above. All right, whatever is easiest to you. But since this is not a nice factoring situation here, I would have tried just plugging in the last 2 values. Okay. All right. So then when we do the quadratic here, okay, so if you would have followed my method and you would have checked out the -1/2 and the -5/2, you would have found out that neither one of those are roots. So you would have had to come and do the quadratic formula anyways. All right. And doing the quadratic formula, it's going to give us our remaining 2 roots. Okay, and it's -1 plus or minus 2i. Okay, and since 2i is imaginary, right, and we've got this complex number with an imaginary number, those won't show up on your graph. So you would only actually have 1 0 on your graph, but you're still going to have three roots. Okay. So then, remembering that polynomials are a degree of n, okay, it can have at most n different real zeros. We talked about how it can have n-1 turns, okay? This might be looking at changing the viewing window, okay? By that, it means where you're looking at on your graph. Because if you've got to deal with an x value that's super, super far away, like maybe -100, okay, you might want to change your window so that you can see it. But For example here, if you were just given this graph here, you could tell that, hey, you've got 1, 2, 3 real zeros because you can see it cross the x-axis 3 times. But since this function is x to the 5th, that means that you have to have at least, you've got to have two imaginary zeros because you've got 1, 2, 3 that you can see. So either 2 are imaginary or they're so far away that you can't see them. All right. So again, talking about zooming in, zooming out, right? This is the example of a graph that I talked about earlier where it's not actually a flat line. If you zoomed in really closely, you would actually see where it crosses the x-axis and that it's actually constantly increasing. All right, same thing here, zooming out, right? If you only had this going from 20 to 20, you would have missed the 0 out here at -50. Okay, so you got to make sure that you're taking into account multiple views on your calculator and not just looking at the first ones you see. Okay. And I know I'm running out of time here, so let me quickly show you these answers. All right. Again, you're gonna follow the process of finding all the possible roots, right? Looking at the equation, looking for those changes in signs, and then trying to find bounds if you can. And basically, worst case scenario, what you can do is you can just plug in values. Once you've eliminated positives and negatives, you can plug in values until you get something with a remainder of 0, meaning that it is a root, okay? And then once you get a root, you can write the polynomial in your factored form, all right? And then you can solve for the remaining roots there, okay? And